Lesson 5.2, Graphing Polynomial Functions. How do you sketch the graph of a polynomial function in intercept form? What we're about to learn. Explore 1. Investigating the end behavior of the graphs of simple polynomial functions. Linear, quadratic, and cubic functions belong to a more general class of functions called polynomial functions, which are categorized by their degree. Linear functions are polynomial functions of degree 1. And when I say degree 1, linear functions look like y equals, and we'll say 4x plus 3. That's a linear function, okay? Quadratic functions are polynomial functions of degree 2. And a quadratic function looks something like y equals 2x squared plus 5x plus, we'll say 7, okay? And cubic functions are polynomial functions of degree 3, and they might look something like y equals 4x cubed plus 2x squared plus 3x plus 5, okay? In general, a polynomial function of degree n has the standard form p of x equals a sub n x to the nth power plus a sub n minus 1 times x n minus 1 plus, and then so on, plus a sub 2 x squared plus a sub 1 x plus a sub 0, where a sub n minus 1, and so on to a sub n, a sub 1, and a sub 0 are real numbers called the coefficients of the expressions. A sub n times x to the nth, and a sub n minus 1 times x to the nth, and so on till you get to a sub 2 x squared and a sub 1 x and a sub 0, which are the terms of the polynomial functions. So let's go up here. The coefficients are 4, 2, 3, and 5. And then on the x squared, it would be the 2, the 5, and the 7. And on the linear function, it would be the 4 and the 3. Those are the coefficients. All right. Note that the constant term a sub 0 appears to have no power of x associated, but since x to the 0 power equals 1, you can write a sub 0 as a sub 0 x to the 0 power and treat a sub 0 as the coefficient of the term. A polynomial function of degree 4 is called a quartic function, while a polynomial function of degree 5 is called a quintic function. After degree 5, polynomial functions are generally referred to by their degree, as in the 6th degree polynomial, the 7th degree, and so on. Use a graphing calculator to graph the polynomial functions f of x equals x, f of x equals x squared, f of x equals x cubed, f of x equals x to the 4th, f of x equals x to the 5th, and f of x equals x to the 6th. Then use the graph of each function to determine the function's domain, range, and end behavior. Use interval notation for the domain and range. So let's see here. Let's do f of x equals x. So we'll just go ahead and graph x. And graph, and we'll just put an x in there. Press enter. So that's what it kind of looks like. Well, that is exactly what it looks like. All right. So what's the domain? The domain is going to be, let me see if we can't quite, let's see. Let's make this a little bit smaller. We'll say 150. Does that gets them all on there? All right. So the domain is going to be all real numbers, and to do it in interval notation, that will be negative infinity to positive infinity. All right. And then the range, the domain is the x values it covers, and the range is the y values. It covers all the y values. So that's going to be negative infinity to positive infinity. The end behavior, as x gets out here and approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, as x gets out here and approaches negative infinity, f of x approaches negative infinity. Negative infinity. All right, good. Now let's try x squared. Let's go back to our graph. And we're just going to, let's see. We're going to make it x squared. X squared. All right. And there we go. It looks like that. Okay. The domain. Look at are the x values, and this keeps on going like that, that keeps on going like that, and it's at an angle. So eventually it'll get it out here to positive infinity, but it's going to get up here to positive infinity a lot faster. So we're going to say the domain is going to be negative infinity, and I was just doing the end behavior on it. Let's go back here. The x values, okay, so it's going to get out here and it's going to get way out here to positive infinity. It's going to get way out here to negative infinity. So we're going to say negative infinity to positive infinity on the domain, because these are at an angle. Okay. Now, what about the range? Notice the range. It starts here at 0 and it goes up. Both legs go up, so the range goes up. So we're going to say it starts here at 0 and it goes to positive infinity. All right, good. Now over here, as it gets out here to positive infinity, it's going to get up there to positive infinity. As it gets out here to negative infinity, it's going to get up there to positive infinity. So we're going to go positive infinity and positive infinity for the end behavior. What about x to the third? X to the third. Press tab. And caret 3. And notice now you got one leg up and one leg down. All right. The domain is going to go all the way out here and all the way out there, because that's at an angle and that's at an angle. So it's going to go, the domain is going to be negative infinity to positive infinity. And the range is going to be negative infinity. Well, that looks terrible. Negative infinity to positive infinity. All right. And you can look at it, see it's going up and it's going down. All right. Now, what about the end behavior? As f of x approaches positive infinity, or as x approaches positive infinity, f of x is going to get up here to positive infinity. As f of x approaches negative infinity, when it gets way down, it's going to be way down here in negative infinity. So positive infinity and negative infinity. All right, let's try x to the fourth. X to the fourth. We'll press tab. And then, let's see, take out the 3 and put a 4. And voila, there it is. Okay. So this is at an angle and that's at an angle. So the domain is going to be all real numbers. It'll go from negative infinity. To positive infinity. The range, notice the range. The range is going to start here at 0 and go up. So we're going to say 0 to positive infinity. And the end behavior, as it gets out here towards positive infinity, it's going to be way up there towards positive infinity. As it gets out here towards negative infinity, it's going to be up here towards positive infinity. So that's going to be positive infinity and positive infinity. Are you starting to notice a trend here? See if you're noticing the trend here. Let's see here. X to the fifth. Well, let's take a look at x to the fifth. And we'll press tab and we'll change that from the fourth to the fifth power. And now, have you noticed x was like, let's just go ahead. We'll put in x What does x look like? And then we'll put in x to the third. Have you noticed all of those? You got one leg up, one leg down. So if it's odd, you got one leg up and one leg down. If it's even, well, we'll talk about that here in a minute. So let's go up here and let's go ahead and clear that off. Control, delete, and then tab, control, delete. All right, so now we're just back to this one here. So our domain is going to be negative infinity to positive infinity. And then the range is going to be, again, negative infinity to positive infinity. And the end behavior, as x approaches positive infinity, f of x approaches positive infinity. And as x approaches negative infinity, f of x approaches negative infinity. All right, now let's x to the 6. All right, and I want you to notice this. What's going to happen here? Okay, that's real similar to x squared and x to the 4th, wasn't it? Real similar. Let's see, x squared. Yeah, and then tab x caret 4. All right, notice how they do there. And let's see, legs are up. It just gets a little flatter down in here. It just gets a little flatter down in there. Tab. All right, good. So what do we got for a domain? We're going to have negative infinity to positive infinity because the legs were at an angle. The range is going to start at 0, and it's going to go to positive infinity. And as f of x approaches positive infinity, or as x approaches positive infinity, f of x approaches positive infinity. As x approaches negative infinity, f of x approaches positive infinity. All right, good. Use a graphing calculator to graph the polynomial functions f of x equals negative x squared, negative x cubed, negative x to the 4th, negative x to the 5th, and so on. So let's see how the end behavior changes. All right, let's see how the domain, range, and end behavior change. So we're going to put in x. Let's put in negative x. Control, delete. We got negative x. Enter. Aha. How did that compare to x? Well, let's just, what happened? It was just reflected. Right? Tab. Just reflected. Okay, so what do we got? We have the domain is going to be negative infinity to positive infinity. The range is going to be negative infinity to positive infinity. And as f of x approaches positive infinity, as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches positive infinity. Okay? And take a look. As it gets out here, it's way down here. As it gets out here towards negative infinity, it's way up there. So let's try negative x squared. All right. Whoa. Okay. See, it just reflected over the x-axis, same as the other did. All right. So what happens here? Well, again, it goes negative infinity to positive infinity for the domain. The range is a bit different now. The range is a bit different. It's going to go from negative infinity to 0. Okay. How did that compare to last time? It went from 0 to positive infinity, And now it goes from negative infinity to positive infinity. And as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, it approaches negative infinity. And what did it do on the other? On the other, it approached positive infinity on both. Now it's approaching negative infinity. All right, negative x cubed. Again, the domain is negative infinity to positive infinity. And the range is going to be negative infinity to positive infinity. And as f of x approaches positive, as x approaches positive infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches positive infinity. And then just take a look. See, oh, they both went to negative infinity. Oh, this is x cubed. That's x squared. Let's put in x cubed. Let's put in x cubed. Delete cubed. All right. See, as it got out here to negative, it was up. As it got out here to positive, it was way down. All right. So x negative x to the fourth. Well, it's going to do like it did over here. The domain is going to be negative infinity to positive infinity. And then it's going to go from negative infinity to 0. And the end behavior, both end behaviors, will f of x will approach negative infinity. Negative x to the fifth, well, you've got negative infinity to positive infinity, negative infinity to positive infinity. And here, okay, it's going to be the opposite, negative infinity and then positive infinity. And here, it's going to be like the x to the fourth and the x squared. It's going to be negative infinity to positive infinity and negative infinity to 0. All right. And then both of these legs will go to negative infinity. All right. Good. Good. How can you generalize the results of this explorer of f of x equals x to the n and f of x equals negative x to the n, where n is positive whole numbers? Okay. The domains of the functions are both negative and, let's see, the domains are both negative infinity to positive infinity for the domains. The range depends, let's see, the range depends on whether n is even or odd. If n is odd, the ranges are negative infinity to positive infinity. If n is even, the range of f of x, well, I'm not writing very well tonight. Range of f of x is 0 to positive infinity if n now let's see. The range of f of x is 0 to positive infinity if a is positive, if a is positive, and we'll say negative infinity to 0 if a, let's say a is less than 0. All right, if a is greater than 0, -1 or something like that. All right, good. The end behavior of f of x equals negative x to the n is always the opposite of the end behavior of f of x equals x to the n. Okay. Investigating the x-intercepts and turning points of graphs of polynomial functions. The cubic function f of x equals x cubed has 3 factors, all of which happen to be x. One or more of the x's can be replaced with other linear factors in x, such as x minus 2, without changing the fact that the function is cubic. In general, a polynomial function of the form p of x equals a times x minus x sub 1 times x minus x sub 2, and so on to x minus x sub n, where a, x sub 1, x sub 2, and x sub n are real numbers that are not necessarily distinct, has degree n, where n is the number of variable factors. The graph of p of x equals a times x minus x sub 1 times x minus x sub 2, and so on to x minus x sub n has x sub 1, x sub 2, and x sub n as its x-intercepts, which is why the polynomial is said to be in intercept form. Since the graph of p of x intersects the x-axis only at its x-intercepts, the graph must move away from and then move back toward the x-axis between each pair of successive x-intercepts, which means that the graph has a turning point between those x-intercepts. Also, instead of crossing the x-axis at an x-intercept, the graph can be tangent to the x-axis, and the point of tangency becomes a turning point because the graph must move toward the x-axis and then away from it near the point of tangency. The y-coordinate of each turning point is a maximum or minimum value of the function at least near that turning point. A maximum or minimum value is called global or absolute if the function never takes on a value that is greater than the maximum or less than the minimum. A local maximum or local minimum, also called a relative maximum or a relative minimum, is a maximum or minimum with some interval around the turning point that need not be, but may be, a global maximum or a global minimum. Use the graphing calculator to graph the cubic function f of x equals x cubed, x squared times x minus 2, and f of x equals x times x minus 2 times x plus 2. Then use the graph of each function to answer the questions in the table. All right, so first let's do x cubed. let's see, tab, and we're just going to do x cubed, not negative x cubed. So there we go. And that's what it looks like. All right. Now let's go and answer the questions. That's what it looks like. What are the questions? All right. 1. How many distinct factors does f of x have? It has 1. What are the graph's intercepts? 0. Okay. Is the graph tangent to the x-axis, or does it cross the x-axis at each intercept? It crosses at x equals 0. Okay. How many turning points does the graph have? 0. How many global maximum values? How many local maximum values that are not global? No maximum values. How many global minimum or how many global minimum values? How many local minimum values that are not global? No min values. All right. And let's go back to it. Okay, so it's got the one turning point. Well, how many turn? It goes here and it is down. Okay, so it's not, the turning point would go back up or something like, or back down or something like that. And it starts up or it starts down and it goes up. So there's no turning points. Okay, and there's no local max or local min. You know, there's the global max is actually positive infinity up here and negative infinity down there, but that's not a particular value. All right, so let's try, and it's x squared, and it's x squared times, and that's x minus 2. X minus 2. And let's see how that changes. Look at there. Okay. All right. X squared times x minus 2. Now, how many distinct factors does f of x have? Okay. On this first one, you had x cubed equals 0. Okay. So that's one distinct. Now you have x squared equals 0 and x minus 2 equals 0. So that's, maybe I should do that in a different color. Let's do it here. So that's 2 distinct factors. What are the graph's x-intercepts? Well, if you look, it comes up tangent to 0 and it crosses at 2. So it has two distinct, or it crosses at 0 and 2. Is the graph tangent to the x-axis, or does it cross the x-axis at each intercept? It's tangent at x equals 0 and crosses at x equals 2. How many turning points does the graph have? It has 2. And let's look. See, it up here and it goes back down, and down here and it goes back up. So it has 2 turning points. How many global maximum values? How many local maximum values? Okay, no global max, no global max, but local, but one local max, and that's at x equals 0. Okay, and let's see. Yeah, see at x equals, and then it's got a local min here, and menu 6, 2, and see it's got a local min at 1.33. So no global min, no global min, 1 local min at x equals 1.33, repeating. Okay. All right. Let's try the third one here. So now we're going to have, let's see, tab and control delete, and we got x times open parentheses, and we got x minus 2, x minus 2, close parentheses, times, and then x plus 2. All right, enter. There we go. All right. Okay. Now that's a little bit different. Okay. So how many distinct factors do we have? How many distinct? Well, this time we have 3 distinct factors. Okay. And let's see here. You got x, you got x, you have x minus 2, and you have x plus 2. Okay. And each of those you can set equal to 0. All right. So we have 3 distinct factors. What are the graph's intercepts? Well, x equals 0, so you got 0. And then if you add 2, x equals 2. And if you subtract 2, x equals negative 2. So we got 3 here. All right. Is the graph tangent to the x-axis, or does it cross the x-axis at each intercept? It crosses at all 3. Crosses at all 3. Notice here you had x squared, okay, and it x squared. Remember, it kind of came up to it. And that was at the origin. It came up to the origin there, and then it went down, and then it went back up at this point 2 here. Okay, so this one here, since there's no squares, it's going to have 3. It has 3 separate factors, and since none of those are squares, it's going to go through the point at there. Okay. How many turning points does the graph have? The graph has 2. It has 1 here and 1 there. Okay. So 2 turning points. How many global maximums or local maximums? And it's got this one local maximum, menu 6, 4. I don't know what I did there. Menu 6. 3 is what I should have hit. I hit 4. So it has a local max at x equals no global max, local max at x equals negative 1 point, what was that? 1.15. And no global min, 1 local min, and local min at 1.15 at x equals 1.15. All right. Let's take a look now. Use a graphing calculator to graph the quotic function x to the 4th, x cubed times x minus 2, x squared times x minus 2 times x plus 2, and f of x equals x times x minus 2 times x plus 2 times x plus 3. Then use the graph of each function to answer the questions in the table. All right. So first, let's do x to the 4th. Tab. And then we're going to do x to the 4th. X caret 4. Enter. There it is. I don't know why that point's on there. Let's just clear that off. New document. No. Graph x caret 4. All right, take a look. There it is. All right, good. let's see. Let's answer the questions. How many distinct factors does it have? How many distinct factors does it have? It has one, and that's x to the fourth equals 0. So it has 1. How many x-intercepts are there? 0. Tangent to or cross the x-axis at the x-intercept. It's tangent at x equals 0. How many turning points? 1. Okay. How many global maximum or local maximums? No max values. And how many global min or local min? No local min. One global, and that would really be at x equals 0 probably. All right, now let's try. Let's see. If you remember on the x squared, it went up and touched it, but it didn't cross it. And then here on the x to the fourth, it goes down and touches it. And let's see, Control T, and you'll see it goes and it touches it, but it doesn't cross it. Now, how's that going to be a little bit different with this next one? How's that going to be a little? So tab. So x cubed times, and then we have x minus 2. X minus 2. Okay, so that's going to be a little bit different. Okay, that's going to be a little bit different. All right, let's take a look at that. So let's answer the question. How many distinct factors does this have? Well, let's see. It has x cubed equals 0, and it has x minus 2 equals 0. So it has 2 distinct factors. Okay. What are the x-intercepts? Well, it looks like 0 and 2. Okay. So we got 0 and 2. Tangent or cross the x-axis at intersect. Crosses at both. Crosses at both. Okay. How many turning points? Let's see. How many turning points? 1, 2. Looks like it's got 2 turning points. Okay. 2 turning points. Okay. How many global maximum values? How many local maximum values? No maximum values. Now, what about local? What about minimum values? How many global minimum values? There's 1 global min, and that's right there. And it doesn't matter what it is. And then no local min. No local min. No local min. Minimum. And reason why it's global is because it never goes past that spot again. Okay. Now, maybe if you had something that did like this, like that, that would be a local min, and that would be a global min. Okay. All right. So now let's try this next one. Let's try that next one. I need to go back here, and we'll press tab, and then we got x minus 2. We need to times, and then x plus 2. X plus 2. And we need to take 1 off of that cube there and make that a squared. Make that, oh man, why do I do that? Make that a 2 right there. And then we'll get rid of that one, the extra one there. All right, let's press enter. Okay, what do we got here? Ah, look at that. That looks pretty cool. Okay, so let's time for new color here. Let's try new color. Let's try new color. So we have how many distinct factors? We have x squared, we have x minus 2, and we have x plus 2. Okay, and you can set those equal to 0 if you want. So what happens here? We have 3 distinct factors. And what are the x-intercepts? Well, if you subtract 2 from both sides, you get -2. That's 0. And if you add 2 to both sides, you get 2. So that's your 3 factors, okay? Tangent to or across the x-axis. Well, it's going to be tangent to the 0 because that's squared, and it's going to cross here and here. So we'll say tangent at x equals 0 and crosses at x equals -2 and x equals 2. How many turning points? Well, let's take a look. We got 1 turning point here, 1 turning point there, and 1 turning point. So we have 3 turning points. 3 turning points. All right. How many global maximum values? Well, there's no global max, but there is one local max at x equals 0. And that's right there. And then what about how many global minimum values? Actually, it kind of looks like there are 2, but these are actually, they go down to the same, and let me show you. Menu 6, 1, and menu 6, 2. Was 2 both times. See, they both go down to -4. So that's actually considered one global min at y equals -4 and no local min. No local min. All right? And that's supposed to be a y. That's a terrible y. Y equals -4. All right. So let's go here. Press tab. And we'll put the last one in. So we're going to take out the x squared, take out the squared part, and we're going to times, and then we've got x plus 3. X plus 3. Enter. All right. Anyway, we don't have to worry about that. All right, so look here. How's this different? How's this different? So time for a new color. Okay. How many distinct factors? Well, you have x minus 2, x plus 2, and x plus 3. So we got four distinct factors. 4 distinct factors. The intercepts, well, we're going to have -3, -2, 0, and 2. And if you set each of those equal to 0 and solve for x, you'll get them. All right. Tangent to or across the x. None of these have a square, so they will cross. Crosses at all 4 points. Crosses at all 4. How about x-intercepts? X-intercepts. It's a little bit more precise. All right. How many turning points? Well, there's 3, and you can take a look. You got 1, 2, and then down there somewhere is the 3rd. Okay. How many global maximum values? Well, let's see here. There are no globals, but you have a local max at this point right here. whatever that point there is. So we'll say no global max, no global max, one local max, and then how many global minimum values? Well, let's take a look. Okay, I don't see one global minimum. There's a that's a local min, and since this is down over here, that is going to be the global because that's as far as it goes down. So one global min and one one global min and one local minimum. All right, good. What determines how many x-intercepts the graph of a polynomial function in intercept form has? Okay, that's we can answer that pretty easy. Each distinct factor produces one x-intercept. All right. What determines whether the graph of a polynomial function in intercept form crosses the x-axis or is tangent to it at an x-intercept? If the factor that produces the x-intercept is raised to an odd power, the graph if the factor that produces the x-intercept is raised to an odd power, the graph will be tangent to the x-axis. If the factor that produces the x-intercept is raised to an odd factor, an odd power, the graph will be tangent to the x-axis. And this is right out of the book, but if we go back and look, what's the power of this? I mean, this is to the fourth power, okay? None of those, but the squares were tangent. The cubes, and whatnot. If you go back and look, okay, an odd power, the graph will be tangent. The graph will be tangent to the x-axis. I'll explain that a little bit better in class, okay? Suppose you introduce a factor of -1 into each of the quartic functions in step B. For instance, f of x equals x to the fourth becomes f of x equals -x to the fourth. How would your answers to the questions about the functions in the graph change? Since each function graph will be reflected across, okay, this negative here will reflect, let's see, each graph will be reflected across the x-axis. So a max value would become a min value, minimum value, and vice versa. This would change the answers to the questions about global and local maximum values. For instance, f of x equals x to the fourth has no max values, one global minimum value, and no local minimum values that are not global, whereas f of x to the negative x to the fourth would have one global max value, no local min or max values that are raised. So it flips it over, and we'll show you. Let's go here and on new document, no, and graph. We'll put in x to the fourth. Okay, see, no global, yet one local min or one global min. And then if you make that a negative, now you have no global min or local min, but you have one global max, okay? And that would be at x equals 0. So that's how that works. Sketching the graph of polynomial functions in intercept form. Given a polynomial function in intercept form, you can sketch the function's graph by using the end behavior, the x-intercepts, and the sign of the function values on intervals determined by the x-intercepts. The sign of the function values tell you whether the graph is above or below the x-axis on a particular interval. You can find the sign of the function values by determining the sign of each factor and recognizing what the sign of the product of those factors is. Sketch the graph of the polynomial function. So you have f of x equals x times x plus 2 times x minus 3. Identify the end behavior. For the function p of x equals a times x minus x sub 1 times x minus x sub 2, and so on to x minus x sub n, the end behavior is determined by whether the degree n is even or odd, and whether the constant factor a is positive or negative. For the given function f of x, the degree is 3, and the constant factor a, which is 1, is positive. So f of x has the following end behavior. As x approaches positive infinity, f of x approaches positive infinity. As f of x approaches negative infinity, f of x approaches negative infinity. Identify the graph's intercepts and then use the sign of f of x on intervals determined by the x-intercepts to find where the graph is above the x-axis and where it is below the x-axis. The intercepts are x equals 0, x equals negative 2, and x equals 3. These three x-intercepts divide the x-axis into 4 intervals. X is less than negative 2, negative 2 is less than x, which is less than 0, 0 is less than x, which is less than 3, and x is greater than 3. All right, so the sign of the constant factor, if x is less than negative 2, the sign of the constant factor, that was a, is positive. The sign of x would be negative, negative, positive, and positive. The sign of x plus 2 would be negative, positive, positive, positive. Sign of x minus 3 would be negative, 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 and positive. And the sign of f of x equals x times x plus 2 times x minus 3. Well, positive times negative, that's going to be, negative, 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 that's going to give you negative. Negative, positive, negative. Okay, positive, negative, that's going to give you negative. Positive, 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 negative will give you negative. And then positive, 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 positive gives you positive. So the graph of f of x is above the x-axis on the intervals. Negative 2 is less than x is less than 0, and x is greater than 3. And it is below the x-axis on the intervals. X is less than negative 2, and 0 is less than x is less than 3. Okay, so Right here and here, it's below. Right here and here, it's above. Sketch the graph. While you should be precise about where the graph crosses the x-axis, you do not need to be precise about the y-coordinates of points on the graph that aren't on the x-axis. Your sketch should simply show where the graph lies above the x-axis and where it lies below the x-axis. So B, all right, identify the end behavior. So what do we got here? What is our degree? What is our degree? What is our degree? You got 1, 2, 3, 4. You have 4 x's. So what is our end behavior? What is our end behavior? Also notice that you got a negative in front of here. So that means that fourth degree, that means it's going to look something like that maybe. So that's going to be negative x or negative infinity and negative infinity. Okay. And the x-intercept, so you're going to have 4, and that's going to be 1, and that's going to be negative 1, and that's going to be negative 2. So there's your intercepts. So that's going to break it up into, let's see here. That's going to break it up into a couple pieces here. Let me see if I can get it. All right, that's about as much as I can get on it. So that was what? Negative 2, negative 1, 1, and 2. So x is less than negative 2, and then it's going to go from negative 2 to negative 1, and then it's going to go from negative 1 to 1. It's going from 1 from 2, and then it's going to be greater than 2. Or that wasn't 2, that was 4. That was 4. So that's going to be 4, and that's going to be 4. All right. So the sign of x minus 4, that's going to be negative, 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 and positive. All right. The sign of x plus 1, that's going to be negative, negative, positive, positive, positive. So that's going to, these are all negative, so that's going to make that negative. Negative, positive, negative, positive, negative. Yeah. All right. And this is going to be, let's see, negative, positive, negative, positive, positive. So that's going to be positive, negative, positive, positive, positive. That's going to be negative, and that's going to be positive, and that's going to be negative. Okay. All right. So the graph of f of x is above the x-axis on the intervals negative 2 to negative 1, and from 1 to 4. Okay, because see, it's positive here and it's positive there. It is below the x-axis on the interval. That's negative, so that's going to be negative 2, and it's going to be negative 1 to 1, and it looks like it's going to be below on that interval there. I couldn't get it all on there. And it's going to be, let me see, let me put these back in there. So negative 2, negative 1, 1, 4, negative 2, that's going to be negative 1 to 1, and greater than 4. Okay, so we know the end behavior is down here somewhere. Okay, we know that. All right, where does it cross the x-axis? It crosses the x-axis at negative 2, negative 1, 1, and 4. Okay, so I got this leg over here a little bit too far, so it's going to go something like this right here. And it'll look like that, sort of, kind of, maybe, close to it. All right. Okay, so let's take a look at this next one. It says sketch the graph of the polynomial function. So what do we got here? Well, let's see here. we've got a is less than 0, so that's negative, okay? And we've got 2 and 1, that's 3. A is negative, and we have a third degree. And so what do we know? As x approaches positive infinity, as x approaches negative infinity, f of x, as x approaches negative infinity, f of x will approach positive infinity. As f of x, that will be negative infinity. So you're going to have a leg up here, and you're going to have a leg down there. Okay, that much we know. Now here we've got x squared equals 0, so x equals 0. Now look at there, that's squared. So we're going to have something that does like this. Okay, it's not actually going to cross. It's going to be tangent. Okay, and then we have x minus 4 equals 0, so x equals 4. So here 4 is going to cross. So it's going to look something like this right here. It's going to go up here. I don't know how far, and then back down, and then there it goes. All right. So there's our. So the graph of f of x is above the x-axis on the interval. X is less than 0 and 0 to 4, and it's below when x is greater than 4. All right, good. Modeling with a polynomial function. You can use cubic functions to model real-world situations. For example, you find the volume of a box of a rectangular prism by multiplying the length, the width, and height. If each dimension of the box is given in terms of x, then the volume is a cubic function of x. Example 2. To create an open-top box out of a sheet of cardboard that is 9 inches long and 5 inches wide, you make a square flap of each side length x inches in each corner by cutting along one of the flap sides and folding along the other. In the first diagram, a solid line segment in the interior of the rectangle indicates a cut, while a dashed line segment indicates a fold. After you fold up the 4 sides of the box, see in the second diagram, you glue each flap to the side it overlaps. To the nearest tenth, find the value of x that maximizes the volume of the box. All right, analyze information. We want to identify the important information. A square flap of side length x is made in each corner of a rectangular sheet of cardboard. The sheet of cardboard measures 9 inches by 5 inches. Find the dimensions of the box once the flaps have been made and the sides have been folded up. Create a volume function for the box. Graph the function on a graphing calculator and use the graph to find the value of x that maximizes the volume. Okay, so we're going to write expressions for the dimensions of the box. So the length of the box is going to be 9 minus, and we're going to have 2 right there. So 2x. The width of the box is going to be 5 minus 2x. And the height of the box is just going to be x. So the volume is going to be 9 minus 2x times 5 minus 2x times x. Because the length, width, and height of the box must be all positive, the volume of the function's domain is determined by the following 3 constraints. 9 minus 2x is greater than 0, or x is less than 4.5. 4.5. 5 minus 2x is greater than 0, or x is less than 2.5. X is greater than 0. Taken together, these constraints give a domain of 0 is less than x is less than 2.5. Okay, because 2.5 is less than 4.5. Use a graph calculator to graph the volume function on its domain. Adjust the viewing window so you can see the maximum. Okay. All right, so let's graph it. Let's graph it. And on new document, no. Oh, I don't know why I did that. Graph. All right, so what do we got here? We have x times, open parentheses, 9 minus 2x, 9 minus 2x, close parentheses, times, open parentheses, 5 minus 2x. And there it is. Okay. And there it is. So it has to be less than 2.5. So we're talking about in here, right here, using graphing calculator to graph the volume function of its domain. Adjust the viewing window so you can see the maximum from the graph. Okay, so menu, 4, out, 4, 4. All right, there it is. Hit escape. And let's see here. I want to menu 4, 1, and x I'm going to put at -1, and we'll just say 4. All right, there we go. All right, okay. And then we want from the graphing calc select the maximum. How do we find this maximum? Menu 6, 3. And okay, so volume x is approximately 21 when x equals 0, or when x equals 1 point. I think it's what was it, 1.03? Yeah, 1.03, which means that the box has a maximum volume of about 21 cubic inches when square flaps with a side length of 1 inch are made in the corners of the sheet of cardboard. Okay. Justify and evaluate. Making square flaps with a side length of 1 inch means the box will be 7 inches long, 3 inches wide, and 1 inch high. So the volume is 21 cubic inches. As a check on this result, consider making square flaps with a side length of 0.9 inches and 1.1 inches. Okay. So the volume of 0.9 would be 9 minus 1.8 times 5 minus 1.8 times 0.09, and that gives you 20.736. Did it in the calculator. And then volume 1.1, that was 9 minus 2.2 times 5 minus 2.2 times 1.1 gives you 20.944. Both volumes are slightly less than 21 cubic inches, which suggests that 21 cubic inches is the maximum volume. 6. Although the volume function has 3 constraints on its domain, the domain involves only 2 of them. Why? All 3 inequalities must be satisfied simultaneously. Any x value that satisfies x is less than 2.5 also satisfies x is less than 4.5. So the constraint x is less than 4.5 has no impact for the domain. Okay, since x is less than 2.5 is less than x is less than 4.5, the x is less than 4.5 constraint has no impact. Has no impact on the domain. All right, your turn. To create an open box out of a sheet of cardboard that's 25 inches long and 13 inches wide, you make a square flap of side length x in inches in each corner by cutting along one of the flap sides and folding along the other. In the diagram, a solid line segment on the interior of the rectangle indicates a cut, while a dashed line segment indicates a fold. Once you fold up the four sides of the box, you glue each flap to the side it overlaps. To the nearest tenth, find the value of x that maximizes the volume of the box. So that's going to be a lot like last time. So you're going to have 25 minus 2x is 1, and you're going to have 13 minus 2x, and then you're going to have the height that's just going to be x. So let's see, add 2x, so you got 25, let's see here, equals 2x, that's going to be 12.5 equals x. Okay, this is going to be a constraint here. So you're going to have 13 equals 2x. So that's going to be 6.5 equals x. Let's see. All right. And so the domain is going to be 0 is less than x is less than 6.5. Okay. And then let's see here. All right, let's put it in the old calculator here. Let's see here. Tab. Oh, it's going to do that again. Tab. And then you're going to have, let's just change this to, this is going to be 25. That's 25. And that's going to be 13. Okay. All right. So let's see. We know that 6.5. So we'll go menu, 4, and we'll just grab it. Oh, it gets way up there, doesn't it? All right. Escape. And then let's just see. Menu, what's the max? 6, 3. It's going to be 402. Okay, so that tells us that the max volume is 402 cubic inches. And with the side lengths of, let's see here, 2.7, with side lengths of 2.7 inches. And that would maximize the volume. All right. Compare and contrast the domain, range, and end behavior of f of x equals x to the n when n is even and when n is odd. The domains are always the same. The domains are always the same. Are always the same. But when n is even, the range consists, but when n is even, the range consists, I can't spell consists x is greater than or equal to, or not, consists of numbers greater than or equal to 0. Whereas when n is odd, when n is odd, the range is all real numbers. All right. When n is even, f of x approaches positive infinity as x approaches both negative and positive infinity. Let's see. When n is even, f of x approaches positive infinity when x approaches both negative infinity and positive infinity. Whereas when n is odd, f of x approaches negative infinity as x approaches negative infinity, and f of x approaches positive infinity as x approaches positive infinity. Essential question check-in. For a polynomial function in intercept form, why is the constant factor important when graphing the function? The sign of the constant factor has the sign of the constant factor has an impact on the end behavior of the function. It also has an impact on whether the y coordinates of turning points represent maximum or minimum values. All right, folks, great job. I will see you tomorrow in class, and you have a great evening.